Hello, today we're going to be talking about moment integrals. So a moment integral, we're going to start out by kind of explaining the idea with kind of discrete parts. So if we were to have a number of forces acting on a beam, so we've got cantilever beam down here, we're going to take the moment about A. To find the overall moment at that point, we would simply add up the moment due to each of these forces. So I'd do the force times the distance for 1, force times this overall distance for 2, force times overall distance for 3, and I would simply add those three things together to get my overall moment. With the moment integral, we are going to do something very similar except with calculus. So for something such as a distributed force, we can imagine this force as a number of very small forces kind of all added together. So we've got an infinite number of very small forces, and the sum of these moments is going to be, we're going to use integration to find that. And so our formula is the integral of all those moments about point A over here is going to be the force function times x. So force times distance, and I take the moment, or I'm taking the moment by kind of summing up all those pieces, which is what integration is for. Alright, so this idea of using integrals to sum up moments exerted by distributed forces, or very similar kind of tactics for areas or masses, is known as the moment integral. So there's many types of moment integrals. We're going to go through a couple of the common types. They're going to be useful for many purposes. So we can use it to calculate the equivalent point load for distributed forces, just like we were talking about before. We can use it to find the centroid or the center of mass for a body. We can use it to determine a beam's kind of resistance to bending. We can use it to determine a shaft's resistance to twisting as we turn that. And finally, we can use it to determine the mass moments of inertia, which are going to be a body's resistance to angular accelerations. So there's lots of potential applications for this, and there's different types of moment integrals were used for each of these. Alright, so the types of moment integrals, there's basically four big distinguishing characteristics of our moment integrals. We can have 2D or 3D moment integrals, and that is a pretty self-explanatory piece of this. We can have area or volume moment integrals, or we can have mass moment integrals. We can have first moment integrals, or we can have second moment integrals. And we can have rectangular moment integrals or polar moment integrals. So any combination, so I can choose 2D, like area, second rectangular moment integral. I could do that. Only some of these are going to be useful though. So we've got a lot of combinations. They're all possible to calculate, but we need to figure out what specific scenario, what specific moment integral we're going to use for each of those kind of applications I talked about on the last slide. Alright, so let's talk a little bit about these distinctions. First is 2D or 3D. This is going to be fairly intuitive. When a 2D moment integral, it's going to be conducted over an area. In a 3D moment integral, we're conducting this over a volume. So usually this one's not listed as part of the moment integral. We just look and see if we have an area or if we have a volume, and kind of deal with that accordingly. Alright, next is going to be area/volume moment integrals for either 2D or 3D versus mass moment integrals. So this deals specifically with the area or volume we're examining, and if we are going to treat every little bit of the area or the volume equally, then we are using an area or volume moment integral. But you can imagine, this can include things like distributed forces, where basically the height of our force curve is equal to the force that's being exerted at that point, the pressure at that point. So we still treat that kind of as an area moment integral. The alternative is the mass moment integral, where we don't treat every bit of volume or area equally. we're going to have kind of a density term that gets incorporated into all of this. So the density term is there because if we imagine something like a wheel, if we have a rubber tire on a steel wheel, the steel is more dense. That needs to be weighted more heavily when we're looking at the kind of forces times distances than the rubber. 1 bit of volume of the rubber is not the same as 1 bit of volume of the steel. So the mass moment integrals are a little more complicated than our area or volume moment integrals are going to be. Alright, next we're going to talk about first versus second moment integrals. So a first, this deals with a distance term, and the first moment integral has a single distance term. Excuse me. A single distance term within the integral. And a second moment integral has a distance squared term within our integral. So specifically this distance squared term is going to be important for mass moment integrals because as we're going to talk about later on with the mass moment integral pages, the relating angular acceleration to moments. So here I've got a mass on the end of kind of a stick. So if I rotate this thing around, starting with F equals ma out here at the mass, I can find that the moment is related to the angular acceleration alpha. It's m times d squared. So I actually need a d squared term rather than just a distance that I have for a normal moment. So rectangular versus polar, first dealing with this in 2D. It deals with how we measure our distances in our moment integrals. So if we're measuring distances from an axis, so how far up am I from the x-axis, how far left or right am I from the y-axis, that's going to be a rectangular moment integral. If I'm measuring from a set point, so say I'm measuring all of my distances from the origin, that one's going to be a polar moment integral. And so this is what, I've got some point out here. If I'm measuring up from the x-axis or out from the y-axis, again rectangular. If I'm measuring out from the origin point, that would be a polar moment integral. Alright, now if we deal with this in 3D, the distances in 3D are all measured from a plane. So this is going to be out from the xy plane, out from the xz plane, etc. And it's going to coordinate kind of with the x or y coordinate again. And the distances in polar moment integrals are all going to be measured in axis for 3D problems. So if I'm measuring from the x-axis, from the y-axis in a 3D problem, that's going to be a polar moment integral. And we kind of see here, it's a little bit hard to see, but I've got kind of a sphere. Again, if I'm measuring out from one of these planes, it's going to be a rectangular moment integral. If I'm measuring out from one of the axes, it's going to be a polar moment integral. Alright, so determining the moment integral, we've got lots of different types, and there's lots of kind of pieces that go into determining all of these. But we've got kind of the same procedure we start with in all of these. So we need to describe a function that's the rate of the change of the area, the rate of change of the mass, rate of change of the volume as we move kind of from one side of the shape to the other, move from the center out, something like that. And this is going to be the function we integrate. We need to first multiply that by the distance. This can be x, it can be y, it can be z, it can be r. It depends on our problem. So we take our original function, multiply it by our distance variable, and then we find the definite integral, and we could be moving left to right, we can be moving top to bottom, we can move from the center out, but we've got some definite integral that we're going to be taking for this moment integral. So with that, that's all I have for moment integrals. I've got a lot more details on the video lectures for each of the kind of useful moment integrals that we're going to do. So thank you for watching, and I hope to see you again.